Projections, radial projections in finite spaces.
So this is joint work with Wang and So I'm going to talk about radial projections. We have a slightly different definition in real space and finite space. Well, actually, first let me say that these are, if you have some kind of fractal set, it could have a fractional dimension, and they're really interested in kind of this sort of metric properties. Given a set where you know that the dimension is not too large, what does it look like from different angles? This is the kind of general idea of the talk. Now, more concretely, if you have a set, a point y and a point x, the radial projection of x from y is, in real space, just the projection of that point down to the sphere that contains, to the d-1 dimensional sphere. You just take the intersection of the ray from y to x with the d-1 dimensional sphere. And for points in finite space, it's just a little bit more convenient to map it to projective space. They say that the projection from the projection of x from y is the line that contains x and y. And if we have a finite set E, or not necessarily finite set, but if we have any set E, the projection of E from y is just the union of the projections of all the points in E from y.
So when you write x comma y bar, that's the set.
That's just the line that contains x and y. So you can think about that as a point in the d-1 dimensional projective space. So the map in real space is a map to the d-1 dimensional sphere. It's a little inconvenient to define it that way in finite space, so instead we map it to just the line that contains x and y. So if there are many points on that line, the image is just that one point. And that's kind of what we're interested in this situation is what are this, from what position, if you have some set in space and you're looking at it from different angles, it's usually going to look almost the same size as what it is in space. But there might be some special angles from which it looks very small, and the question is, how many special angles can there be? Or how many special directions? How many points in space can there be where the projection looks very small? So, the general philosophy is that the radial projection of a set is usually as large as possible. How large can it be? So if you have, say, if you know what the size of the set that you're looking at is, so it's either the Hausdorff dimension of E in real space, or it's the cardinality of E in finite space, then from most directions, the projection is not going to be much smaller. It'll have the same dimension or the same cardinality. Unless the set is so large that when you project it down to a d-1 dimensional space, it doesn't fit. So there's kind of two different situations. One is that the dimension of E is larger than d-1. Well, d-1 is the largest size of that's the largest thing that you can see. Similarly, if you're in finite space, there's only q to the d-1 points. So here, kind of the correspondence between dimension and cardinality is the log base q, where q is the order of the field you're working over.
So do you assume that E is a finite set or E is a space?
So there's two different settings that we're looking at. In the work that we did, E is a finite set in a finite geometry. But all of our results are kind of related to corresponding results and conjectures in fractal geometry. And here, E is a Borel set. And so in the finite case, we control the cardinality of E. In the continuous case, we control the Hausdorff dimension of E. And these are, for this question, these things, there is a very clear analogy, and it does seem to hold through most of the results. At least all the ones that I'm going to talk about today, the analogy works the way that you hope it would from the start. So there's kind of two different settings for how large your set E is. First is if the dimension of E is greater than d minus 1, then an exceptional point is one from which the dimension of the projection is less than d minus 1. Because d minus 1 is the largest object that you can see. So here, theorem of, in the continuous setting, there's a theorem of Orponen who said if the Hausdorff dimension of E is greater than d minus 1, then the dimension of the exceptional set is at most 2 times d minus 1 minus the Hausdorff dimension of E. And so there is a construction that achieves this, and you can kind of see that it makes sense that the exceptional set would get smaller as the. So if actually let me pass over the constructions for this setting. So we have an analogous theorem over finite space. Here, if you have a set of points in a d-dimensional vector space over a field of q elements, and E is larger than q to the d minus 1, then you know that every projection is bounded above by roughly q to the d minus 1. And so there's slightly more points in, if you take q fairly large, that's a good estimate for the number of points in a projective, d minus 1 dimensional projective space. So the number of points from which the projection of E is much smaller than you would expect. So at most a quarter of what you would expect is bounded above by, again, this is basically 2 times q to the d minus 1 divided by E. Except that in our case, we're a little bit stronger than the most natural analog to the continuous theorem in that we have this parameter n, whereas previously there was a d minus 1 here. So this kind of leads us to a conjecture in the continuous setting, which is that we could substitute in place of f d minus 1 in the dimension of the in the definition of what is the exceptional set that we're looking at. We can consider a stronger constraint on the exceptional set and say, well, how many points can there be, or how large can the set be where our greater than d minus 1 dimensional set looks like an s dimensional thing, where s here is less, at most d minus 1. So this is some generalization of the theorem of Orponen. And I'll say, yeah.
Did you try to prove this conjecture yourself?
In the continuous setting?
Yeah.
No, we didn't really try. We did talk to Orponen, and in fact, he has they did manage to prove it. Orponen and Shmerikin managed to prove this conjecture in the 2-dimensional case, and I'll say a few more words about that later. But it seems like to push it, they used quite a deep recent theorem that is not available in higher dimensions. So I think that there's quite some barrier in that, in pushing it further.
So can you give some intuitive explanations of like Hausdorff type dimensions? I mean, I don't need for my
So the idea is you have some kind of fractal set. So maybe take your favorite fractal set, which might be like, start with a unit interval, delete out the middle third, etc. repeatedly. Now, what is a feature of like a one? What you might think of as the same. You're going to get some number that's not 0 and it's not infinite, and it doesn't go larger. And similarly here, if we cover this guy with balls, the thing is, if we take the first power of the balls and take them smaller and smaller, actually it's going to go to 0. But if we take some, say, log base 2 of 3 power of the balls and take them smaller and smaller, then again you get some finite measure that's between 0 and infinity. And so that means that the dimension of this particular set is log base 2 of 3. And so it's a way that you can kind of get, so that's kind of the very roughly, that's the idea. To define it more precisely is, there are some pitfalls that you would have to get around. So the other kind of setting, so we've got, if we're thinking, there were two different upper bounds on the size of the radial projection. One is d minus 1, and one is the dimension of E. So there's two kind of different natural settings for what is the exceptional dimension. One is when the dimension of E is large, greater than d minus 1, and the other is when d is small, less than d minus 1. So here in the continuous setting, we have, again, this is the most natural definition for what the exceptional set would be. And he has two different upper bounds. One is the same as what they had in the large set, but of course the definition here is different. And the other one is the Hausdorff dimension of E plus 1. But Liu and Orponen don't think that this is the correct answer. So here there's quite a natural and simple explanation for the conjecture. And what the conjecture is that if you have a set that's between, say, k dimensional and k plus 1 dimensional, and k plus 1 is at most d minus 1. So this is a small set E, and it falls in the size of the dimension of the set falls into some integer range. Then the bound on the size of the exceptional set is exactly what you would have. Kind of one way to maximize the size of the exceptional set is to put everything into a lower dimensional subspace. So for example, here we have just stick some set in a line. Then if the dimension of this set is greater than 0, then the kind of exceptional set is every point on this line. So I've kind of put a summary of the situation on this next slide. So the dark blue line, the thick dark blue line is the theorem. It's kind of the combined theorems. So in this last segment here, the definition of what the exceptional set is that this is the set of points from which the projection is not everything in the space, or it's much smaller than the entire space. And so here this bound is known to be tight. And then in the remainder, there's a conjecture and bounds that are different. So here we have, so the upper bound is Liu's theorem. There's kind of two different sections, and then so that's the conjecture, and that conjecture is corresponding to, you just put everything into a low dimensional subspace, and then as long as you're inside that subspace, if your set is inside a plane and you're looking at it from another point in the plane, then your set is going to be contained in a line. And so if the set you started out with was more than one dimensional, then this is the kind of exceptional. Your exceptional set is all the points in the plane. So the next, our first theorem for small e, it is a proof of the finite analog of Liu and Orponen's conjecture only for the very top. So if I can, I'm just going to draw it here. Basically what we get is this segment. So if you have a set of points that's much smaller than the number of points that fits in a hyperplane, and you look at this set of points from which the radial projection is much smaller than the set itself, then this is not much larger than the number of points contained in a hyperplane. So this is up to the value of the constants. This is exactly what we would expect to be true there. And so this proves the kind of the top range for Lund and Orponen's conjecture, the finite analog of it. And just to make a comment about the constants, these are not the main focus of our work. They do come out of, this is like a special case of something more general that gives explicit trade-offs among the different constants, and that I would say that more general theorem is what our proof gives. We don't necessarily think that everything is tight, but you would need some additional idea to get much better on the constants. So in the case that the dimension of, so this theorem, although it doesn't give a good result when the cardinality of E is much smaller than Q to the D minus 2, because then we kind of expect that the exceptional set would be even smaller than this still. And in that range, we don't have we don't have the course. What we have is something that more or less corresponds to Liu's theorem. Again, we have if we think about C as being a constant here, we say if here the exceptional set are those that say let's say 1/2 of E, then the size of the exceptional set is bounded above by Q times E. And that compares to the dimension of E plus 1. So this is stronger than Liu's theorem in the kind of the same way that our large E theorem was stronger than Orponen's theorem. But here, I don't think we would, I don't think it's necessarily worth to think about in the continuous setting what happens when we have when C is larger than a constant, because we just don't think that this theorem is anyway tight even when C is a constant. So it's possible to get better bounds if we assume, so for the small e, everything is corresponding to, well, if we put everything in a low dimensional space, then all the points inside that space only see, if you put everything into a k-dimensional subspace, then no matter what the dimension of that set is, if you take any point inside that k-dimensional subspace, you see a k-1 dimensional set. That is what the conjecture for small e corresponds to. But you can, for many applications, and there are a variety of theorems in this direction, if you just assume that E is not contained in a low dimensional subspace, then you would reasonably hope that every projection is going to be larger. And this is, there are some results in that direction. I think is a very deep and interesting direction of research, and even in the finite case, we don't have the strongest possible bounds. But just in the interest of time, because I want to show a proof, I'm not going to state these, I'm not planning to state these results today. But just to say, there are quite a few results in the continuous setting in this direction, and also we have corresponding results in the finite setting. So we basically, before we, I'd say about a month before we put our paper on archive, we talked to Orponen and mentioned our conjecture, and he said, yeah, I think that it seems like it should be true, and maybe we can make progress with existing methods. And so 1 month after we put our paper on archive, Orponen and Shmerikin did manage to prove our conjecture in the two-dimensional case. And actually, they derived, as a consequence of this theorem, they derived the conjecture of Liu and Orponen, again, only in the two-dimensional case. And their proof is, I mean, it's, I would say, quite a bit more difficult than ours. I'll go ahead and show our proof, and you'll. But it relies on the recent incidence bounds from Fu and Ren in 2021, who considered some type of a bound where you have a lot of small balls and small tubes in the plane, and give a bound on kind of the measure of the overlap between these two sets. And so this is, we do have like good, we have an analog to this theorem over infinite geometry, in fact it's not very hard, and we have it for all dimensions. But it's quite difficult in the continuous setting, and so they don't really have, it's a major open problem, I think, to prove higher dimensional analogs to this theorem. So what I'm going to do now is switch to using the chalkboard. What I want to do is show a proof of this theorem here. Wait, this theorem here. That proves the finite analog to Lund and Orponen's conjecture for sets whose cardinality is between q to the d minus 1 and q to the d minus 2. But I'm going to do that on the blackboard. So if we can move turn off the camera and move the board up. Can we
It's
do
okay.
Okay.
You want to use both sides or?
Yeah, I want to use both sides.
There's a switch.
Switches here. Thank you. I didn't know what was there. Okay. So let me just fix some notation. E is going to be some set in finite space. T is going to be the exceptional set with regard to E. So it's the set of points Y, so that the projection of E from Y has size at most 1/10 E. And then, so for some line L, I'm going to use E of L to denote the number of points of E on L, T of L to denote the number of points of T on L, and L of X is just the notation I use for the indicator function for the point X is contained in L. And then L is a set of lines that contain at least 1 point from each of E and T. And yeah, and G is just a set of all lines. So I do kind of fundamental, very, in this context, quite a simple but fundamental results that are a very useful tool, I would say, for this type of problem is the following kind of incidence type of bound. Let me just write it and then I'll say a few words. We take a sum over all the lines of the number of points on that line minus the expected number of points. So E is some finite set. This is the number of points that you would expect if you chose a random line. You have some finite set, you choose a random line, this is the expected number of points on it. But E is not a random set, and what we're doing is taking the sum over all lines in space of the difference between the number of points that are actually on that line minus the average number. So this is kind of like a variance. We get the following upper bound on that. Q to the d minus 1 over Q minus 1. This is just the number of lines through the origin. So number of one-dimensional subspaces times cardinality. So if there probably will be time at the end, I'll give the proof of this, but I want to give the proof of the theorem first, and then if time allows, I'll give the proof of this. There are a number of different proofs. Like I used to prove this kind of thing using spectral graph theory, and then some more, like it's not the hard consequence of the expander mixing lemma. And maybe for some more sophisticated settings, you'd still do that. Or I've seen proofs using like discrete Fourier analysis. But there's for this particular theorem, there's actually a very, very simple proof where you more or less just write everything out, do the calculations carefully, and the result falls out. So I'd like to show it if there's time.
Who's randomized it?
This is, I guess the first proof that I'm aware of is by Hirschfeld, I think, from 1979. The proof that I give would be from Murphy and Petridis from Luxembourg recently. But yeah, it's not. I should say this is equivalent to. There's another formulation. This is exactly the statement that we need, and it's actually a little easier to prove. But there's another formulation where you have a set, say E of points and a set L of lines, and you look at the number of pairs of a point of E and a line of L, where the point is contained in the line. So there's a very classical kind of incidence-based result where you say the difference between the number of incidences between an arbitrary set of lines and an arbitrary set of points versus kind of the expected number of incidences if these were random sets of lines and points is not too large. But this is, and this is an equivalent, is equivalent to that. But so here's the theorem that I want to prove is that if the cardinality of E is at most 1 over 100 times Q to the D minus 1, then the size of the exceptional set is at most 8 times Q to the D minus 1. So the proof, we're going to give an upper and lower bound for this, the following quantity. Recall L is the set of points that contain at least one point of E and one point of T. So we'll take the sum over all these lines of the number of points of E times the number of points of T contained in that line. And I want to say, first of all, there's a very easy lower bound of the number of points of E times the number of points of T. So this, on the right side, we have the number of pairs of a point of E and a point of T. And each of these is counted at least one time on the left. So if they're distinct points, then there's a unique line that contains them. And so it's counted in that line. And if they're the same points, if you have a point in E and a point in T that are that these are not necessarily disjoint sets, then that line would be counted many times. So this is so this inequality may be strict or may be So the rest of so the main part of the proof is just to come up with an upper bound on that. So what we're going to do is for the upper bound, we'll break this sum up into 3 different parts. First, first we have lines that contain only one point of E. So next we have lines that contain at least 2 points of E and not too many points of T. So not too many here means, well, I'm just going to use some constant C. This C is going to be greater than 1, and I'll choose it later. So we can check later on to make sure that there is a choice, but as long as there's some choice, then I'll be okay. Both E and T are relatively large. So it contains at least 2 points of E and at least C times T divided by Q to the D minus 1 points of T. So let me name these. I'll name this I. Oh, that is not the right way. I. Okay. I. So the first one we found I. We got some. Okay, E of L is equal to 1 times the number of points of T on there. Well, this is at most sum of just all of the points in L times the number of points in T. We already used the fact that E is equal to 1 just to drop the term. And this is equal to the sum of over the points in T of the number of lines of L that pass through it, and that's just the size of the radial projection. So but we have a bound just we have a bound of, right, when we define T here, we have a bound on the size of that radial projection, so we can just plug that back into over here, and so this is at most cardinality of T times 1/10 times T. So this looks pretty good because our lower bound is E times T, and this is E times T over time. So we're kind of moving in a good direction. The second term is at least 2 points of E and not too many points of L, T. So of course, we'll just use this bound here to pull out the T. But then, because we're only counting points that contain at least 2 points of E, each pair is going to be counted just once. And so this is less than c times t over q to the d minus 1 times e squared. And here we also have, here we'll use the assumed upper bound on the size of e, which is 1 over 100 times q to the d minus 1. So this is at most c over 100 times t times e. So now we have some constraint on c that it has to be less than like 90. Because this plus this, it better be less than e times t. Now, I'm just going to hide this because I think these two are quite simple.
You can move it below.
Okay. Try this. All right. So now the third term. Let me just call this L and L prime. And L prime is defined according to these constraints. So both E and, so these are lines that contain many points of E and, or at least 2 points of E and at least a few points of T. And here I'm going to use Cauchy-Schwarz to separate the E from the T. So now we bound each one individually. The easier one is, or we use a more trivial bound for the E of L. So these are lines that contain at least 2 points of E. So we think about this as counting pairs of points, both not necessarily distinct and with the order. So we may have pairs of points that are the same, and we can also have pairs of distinct points. And the point here is that, of course, distinct points, there's only a single line that contains a pair of distinct points. So in this case, every line contains at least 2 points of E. So in particular, there's at most E points through each point of E. So this is bounded above by E squared. And similarly, these are, because no line contains more than, or every pair of points is only contained in a single line, this term is also bounded above by E squared. So this is at most 2 times E squared. And I'll just mention real quick that if we bound this set the same way that we are bounding, that I'm about to bound T, the other sets, or this T of L squared. If we bounded E of L squared the same way that we bound T of L squared, we would actually recover the finite analog of Liu's bound. So somehow by using just a more trivial way to bound this part of it, we get that's where kind of the improvement, the quantitative improvement comes from. But it still remains to bound T of L squared. I'm just going to, well, let me.
Can you explain this equality a little bit? So I don't.
Right. Let's see. So this is. Where's the errors? This is sum over lines of pairs x is equal to x prime of does the line contain x? And yeah. And this is equal to sum over L of the number of, or I guess we can change the order of summation, sum over x in E of sum over lines in L, lines that contain E of L is at least 2 of the indicator for L contains X. So here it is, this is summing over E things, and each sum end is at most E minus 1. And that's where the upper bound of E squared comes from. So here we split apart. These are ordered pairs of.
Oh, in the square term.
Yeah, this is ordered pairs actually. So this more precisely, this would be x and x prime ordered in E squared such that x is not equal to x. So we're just splitting apart those. This is counting pairs of points that are contained. The square of the number of points in L is counting pairs of ordered, not necessarily distinct points that are contained in L. So this is the not necessarily distinct part, and it's important to include because actually we do use we're using part of our assumptions here, which is that each line contains at least E points, or at least 2 points. So this is it's kind of a non-trivial thing that this is actually bounded by a function of E. Non-trivial, it's just that it's because we removed all the lines that only contain 1 point of E to start with. So that's how this is. Yep. And then over here, it's just 2 points contain only 1 line, and that's how everything is bounded by E squared. Now, for the other one, I'm just going to do. So now we have the sum of T of L squared, and the assumption is that T of L is at least C times cardinality T times Q divided by Q to the D minus 1. Now, something I want to kind of point out here is that since we have T of L is at least C times T divided by Q to the D minus 1, we have this T of L minus T of L divided by C. And here, this is the same C that we've been using, and it's going to be greater than 1 squared. All right. And so then this term is looking exactly like this term down here, although the sum. So the plan is that we're going to get this thing inside of our sum, extend the sum to all lines from the set of lines that we started with to the set of all lines in the space, and then use this kind of incidence-like bound. So the natural thing to do is just pull out the term so that what's left over looks like that. T of L, so now we extend, so this sum is over, this sum still has this condition. We use the condition to get this inequality over here, and then we forget about it and extend the sum to all of the lines in the space. And once we've used we're going to use the condition here and then forget about it. And now we use this incidence bound here, and so we get q to the d minus 1 over q minus 1 times 1 minus c inverse 1 over, times t. I'm sorry, I kind of ran out of space here. I'm just going to write it on the next line. So here's the 1 minus, here's the term the constant term we pulled out. And then we have these terms down here. And that's what we have here. So now we have 3 terms, and if we combine them all, what do we get? We've got E times T is at most the sum of EL times TL is at most. So term 1 is 1/10 E times T. Term 2 was C over 100 times E times T. And the third term is the square root of this thing times E squared. So there we get 1 minus C inverse times E times, I guess, is the square root of 2 here, times square roots of q to the d minus 1 over q minus 1. This is basically q to the d minus 1 that we just write. Q to the d minus 1 over 2 times t to the 1/2. So here, the e's cancel out. These terms are just additive, and they kind of feed into the constant term. This is again a constant for appropriate choice of c here. And what we get is everything cancels out except for q to the d minus 1 time and the constants. And that is the end of the proof. So there's 5 minutes left, and I won't, so let me just take questions. I'll just take questions for a remainder.
Do you also think about algorithmic questions like, given, can I want to find T is empty or not, how big it is?
We haven't thought about these questions, so I think that the reason that we started thinking about these questions in particular is that there's this kind of well-established analogy between fractal geometry and finite geometry, And in particular, some of the progress on this type of question over fractal geometry has led to some progress, particularly on, say, the dimension of distance sets. But, say, has led to progress on other geometric questions where we don't really know the answer over finite fields. So the kind of next step is to think about can we apply any of these results to get corresponding improvements on the combinatorial questions that we're interested in over finite geometry. Now, I just don't, I haven't thought at all about the algorithmic questions. I'm not sure. I mean, I just don't know. Yeah, I haven't thought about it at all. And there are many, yeah. Yeah, I just haven't thought about it at all. Let me not say anything more. I just don't, yeah. But there are many algorithmic questions like trying to figure out if a point is, say, what's the, given a set of points in some space, how many points are contained in a hyperplane, and all these kinds of things. Yeah, there's. But both in, yeah, I just don't know. Sorry.
We have more time. Can I ask another random question?
Yeah.
So does it have anything to do with the graph?
Does it have anything to do with graphs?
Yes. Any question in graph theory?
Yes. So here, this question, this result here, you can think about what we have. Think about the point line incidence matrix of finite space. Then what it's claiming is that this kind of the encoded claim in here is that this incidence matrix in some sense is a good bipartite expander. So it may not be balanced, but if you take a large set of lines, then and you take any sufficiently large set of points, then the number of edges in between them has to be about what you would expect, or something like this. So this, I mean, now if E is very small, this is going to be kind of a trivial bound. But for large E, this is giving some. There is a relationship to to say the eigenvalues of this, or the eigenvalues of the square of the adjacency incidence matrix of the finite space. And so you could probably compute it from this, although the proof that I have in mind is a lot more direct. Otherwise, so there's kind of this incidence graph where you're thinking about points and lines, and a point is adjacent to a line if they're incident. So yeah, there's this graph is really in the background all the time through this whole area. Yeah.
Questions?
Any other questions? If not,
do you intend to continue proving the lemma, or?
I can prove it, but I don't want to keep people here who don't want to see it. It would take me 5 minutes, but or maybe 10 minutes.
What do you want?
Do you want to see a proof? Okay. Since this is a proof due to
No, it's behind the first blackboard, the top one.
Right.
If you lower it, then you can find it.
Anyway, I learned this proof by reading a paper of Brendan Murphy and Jorgis Petridis, and it's a little bit less flexible than some of the other ways that I know how to prove this, but it's also much simpler. So let me first write down an expression for the sum of E of L squared. And what I'll do is just the same thing as before. Split out the, I'm just going to get my piece of paper just in case. I think this is going to be exactly the same as what we did over there. This sum of L plus sum of x not equal to x prime, sum of L x prime, and this is equal to, well, here we're summing over all lines, whereas before we only this is what I was saying, that being able to use this constraint is really, that we're only summing over lines that contain at least 2 points is really a kind of critical part. And actually, in the whole proof, this is what gave us the advantage over kind of the direct analog of Liu's proof. But here we're summing over all the lines, so we get q to the d minus 1 over q minus 1. Times e plus x minus 1. So that's just a direct expression for e of L squared. Now we expand this bracket. So now we have e of L minus cardinality e divided by 1 by q to the d minus 1 squared is equal to sum of e of L squared minus 2 times e divided by q to the d minus 1 times sum e of L plus G is the set of all lines. That's here the sum is ranging over all the lines in the space. So there's G things in the sum times E squared times Q to the 2 minus 2. Now my claim is that these two terms, like if you cover up this 2 here, these two terms are the same. Because here this this term, well, we already bounded it. So this is minus 2 times e squared over q to the d minus 1 times the number of lines that contain a fixed point. And then, well, how large is G? G is q to the d minus 1 times the number of lines that contain a fixed point. Q to the d minus 1 is the number of translates of a line that are contained in space. So this is the total number of lines that are in the space times e squared times q to the 2 minus 2d. Well, this cancels out one of these guys. So we get 1 minus d here. And now everything looks the same, so we've got, this term is just twice this term. So if we're going to continue from above here, we've got, this is equal to sum of E of L squared minus E squared times Q to the 1 minus D times Q to the D minus 1 over Q minus 1. Well, E of L squared, we've got the expression, where do we have the expression? Up here. It's the number of lines through a fixed point times E plus something that's less than E squared. Whereas this term here is something that's slightly greater than E squared. So we can just get an inequality here and get Q to the D minus 1 over Q minus 1 times E. Yep, 5 minutes. And I know it looks very trivial, but you know, somehow we had much more complicated proofs before, or I only knew more complicated proofs before. All right, that's all.
Right. Okay.